Hej och välkomna till det här första passet på biennalen. Och det är mitt stora nöje att få introducera Joe Boaler, professor vid Stanford University. Ni känner säkerligen igen namnet och personen utifrån ett flertal böcker som är översatta på svenska, såsom Elefanten i klassrummet, och vi har dynamiskt mindset. Och, så jag tänkte bara snabbt säga varmt välkommen till professor Joe Boaler. A warm welcome to professor Joe Boaler.
Thank you, Andreas, and thank you for coming. I started my career as a teacher in London. That's a picture of me teaching in the red shirt many years ago in a school in Chalk Farm in Camden Town in London. And I went from there to King's College, where I did my PhD in London, and eventually moved to Stanford, where I've been for the last few years. And at Stanford, we made a website. Has anybody been to this website? It's called UCubed. Just see out there, yay, UCubians. So our website is where we share lots of free lessons and tasks. You'll see some things in a minute. And the newsletter's opened in over 160 countries, so it's very international. Always happy to have international visitors. Sometimes people from Sweden come to our workshops at Stanford, which I love. But I wanted to start today by telling you about a program we have at Stanford, which is a summer camp for students. And we have this summer camp because we know that most students don't get the maths experience that they should have. And we wanted to change maths for students from this list on the left to this list on the right. And sometimes it's hard to make those changes in the school system where teachers have lots of demands. So in our summer program, the very first one, we invited students to Stanford for the first one. We had them for 4 weeks, and we decided to focus on 4 big ideas: number sense, learning to generalize, algebra as a problem-solving tool, not as solve for X, and seeing maths as patterns and pattern seeking. A couple of other things that informed our teaching that I wanted to share with you before we watch some. In mathematics education, all the researchers are agreed that mathematics is a conceptual subject with interesting connections. But many teachers say, I don't have time to teach conceptually. And so these researchers did a study with 5th grade teachers, where half of them did what teachers said they could do, which was teach 5 lessons from their textbook, and then have 3 lessons where students learn conceptually with geoboards and tiles. They were learning about area and perimeter. They contrasted this with the other group of students who just got the 3 conceptual lessons. And what they found, and this has been found repeatedly, is the students who just had 3 conceptual lessons did better than the students who had 8 lessons. So this is great for teachers, more time. Now you can just teach 3 lessons and have more time for other things. But the researchers pointed something out important. They called it cognitive interference. I don't know what that is in Swedish, but they said for the students who learned all the methods and rules, when they got to the conceptual lessons, they couldn't think conceptually. Their minds were so taken up with rules that they remembered, they weren't able to think conceptually about the ideas. And this term, cognitive interference, applies all through mathematics education. Sometimes we teach students things that block their thinking. I often in elementary school see teachers do amazing work with number sense and visuals, and then they teach students an algorithm, and it's like all that sense-making disappears. Have you seen that? Students are just focused on the algorithm. So we were thinking about this, and what researchers have found is rather than saving conceptual tasks until the end, it's better to start with those conceptual tasks. Even before you teach students how to do them, give them something to think about, they use their intuition, they connect with knowledge, and then when they're in the task, you can teach them methods that they need. So this was our approach of our summer camp. In the first one, we brought 84 students to Stanford. And on the first day, I went to all the classes, 4 classes, and told them what I'm going to tell you in a minute about mindset. And then we taught conceptually. So these were the 84 students when they took a test before they came to us. Each one is a bar on that graph. Some students had got 0 on that pretest. Some were high achieving. We taught them for 4 weeks, and then we gave them that test again. And we saw massive improvements for students, equivalent to 2.8 years of school. So what did we do in that 4-week camp? I'm going to show you a little film. And I really like this film because you hear from students in their own words what often holds them back in maths and how we change that for them.
Some people think I'm not good at math. I can never do anything. I'm not good at it. I'm just going to give up.
A lot of people think of it as like prison, like you don't have any freedom.
Okay, time to go to your notebook. Okay, read chapter 1. Okay, here's your worksheet.
The math textbook is kind of like the Bible. You have to kind of worship the textbook, and I don't really like that.
Everybody's going so quickly, and I thought if I didn't go quick, people think I'm like not smart.
I made a lot of mistakes, and I got really sad about it.
You make a mistake, you're pretty much done. Yeah.
They can't do it fast, and they're so smart because they can, and I'm not smart, and I just kind of stopped.
You feel like you're serving a sentence for like nothing.
I love it. That does look like a cuboid.
Oh, we got it!
I've done better with math when I was talking with people, sharing ideas.
4 or 5 brains work better than 1.
I'll see it one way, but then someone else will see it another way, and I'll be like, oh my gosh, that makes so much sense.
I love that we're getting different answers out because lots of problems in math, there are different answers.
Have more than one way to solve the question. Because in real life, you're not gonna just do one thing. You're gonna do many things. You're gonna need to use different methods.
Yay!
No, hold on. Take your time and just experiment with every way that could possibly work.
You definitely have to be patient because certain problems, they take forever.
Math isn't about speed, and you can make mistakes and you learn from them.
Yeah, I did that too!
Yes!
Told you!
Math isn't like the enemy, and it can't hurt me.
You can run wild, you can pass ideas by each other.
I thought that math was all about right answers and wrong. Now that I believe that math is really about ideas and creativity, it's a lot more inspiring.
So that was our first summer camp. You just saw Dana in that clip going, yes, I did that too. Dana is now a student at Stanford and talks about how that middle school experience really changed her whole math trajectory going forward. Since that camp, we've been giving teachers the curriculum. They come to our workshops. Some of them are online. We share the curriculum. It goes from kindergarten up to grade 9 or 10, years 9 or 10. And we studied the camp impact in all of these different states across the US. And we found that regular teachers teaching the camp got just as big a boost as we did. The longer the students are in this environment, the greater the boost for their achievement. And then they went back to school and got significantly higher maths grades the following year. In different districts, some people have used the younger materials with younger students. They also see massive increases for the students. 2 years ago, I was invited to Naples to teach undergrads, to teach our camp. And that was really interesting. First of all, Naples had just won this big football competition like the Premier League for the first time in a long time. And everywhere we went, there were images of Maradona coming down from heaven, giving them the trophy. It's very symbolic, lots going on there. But these undergrads were interesting because they were shocked to see maths as a creative, open subject. And then they did a great job with the students. You can see some here. Kids don't want to stop working when you do maths in this way. You see them in the summertime continuing on, at break time, I mean. So we use tasks from a book series we have. It's called Mindset Mathematics, filled with rich tasks for every grade level. So what happened to those students? I want to share with you the messages I shared with the kids on the first day that really helped open them up. And this is a message that we always share, that this is not how it works. But we know that most students do think this is how it works, and they think you're born with a maths brain or you're not. And when they start to struggle, they think, oh, I don't have a maths brain. So I always share with all students, whatever age, and this comes from neuroscientists I work with at Stanford, that there's one of 3 things that happen in the brain when we're learning. You're either forming a new pathway, you're connecting pathways, or you're strengthening pathways, and nobody is born with these pathways. And that's a really important message for kids. All the time they're with you, their brains are growing and strengthening. I also share with students cases of people. This is an interesting one. Nicholas Letchford grew up in Australia. That was him in first grade, where his parents were told he was the worst child they'd had at the school for 20 years because he couldn't read or write. They said he had a low IQ. But Nicholas graduated in 2018 with a doctorate in applied mathematics from Oxford University. And his mother has now written a book about their story and how she refused to accept these labels that were put on him. And we have many, many cases like this, that people, even with the most severe learning disabilities, are able to get to the highest of levels. So a big message of my work, and this book in particular, is to be limitless. When scientists try and find a limit of what students can do, they always come away saying they couldn't find one. People can just learn more and more and more difficult work. So mindset is so important for us as teachers as well as for the students. And a key part of having a growth mindset is really learning to feel good about times of struggle and times of challenge. It's a very big message inside mindset that, we want to be struggling. That's when our brains are really helped. But how do we embrace struggle? How do we get kids to feel good about struggle? You probably have students who don't feel good if they're struggling and start to think, no, I'm not a maths person. Well, I've worked with some amazing teachers who've done a really good job of encouraging struggle. This teacher, Jen Schaefer, is a 5th grade teacher in Canada, and she has this on Post-it notes around her room, the steps of struggle. She tells the students, you want to get onto these steps. You don't have to be the cocky kid on the top step, but you don't want to be the sad one on the bottom step either. And she says the students like this metaphor. There's one they like even more, which is the pit, or the learning pit. And this is a visual that her 5th grade students made, where you can see as their students are going into the pit, they're saying, I'm so confused, I can't do this. But as they're coming out of the pit, they're saying, you know, I need tools, I can learn this. And a lot of great work is done around this learning pit metaphor for students. Jen, when I interviewed the teacher, she said to me that often her students come to her and say, Miss Schaefer, I'm really in the pit. And her response to that is, excellent, that's great. What classroom tools do you need? She doesn't jump in and help them and take away the struggle. She just makes sure they have resources to help. So this is a key message of my new book, which is called Mathish. All of us, as adults, for children, this is the place you want to be. It's called the edge of your understanding, where you're making mistakes, fixing them, keep going, make more mistakes. That is the zone where your brain is on fire with growth. This is where creativity lives. Any new knowledge we want to get to, we need to be walking on that edge. So we shared with students that a growth mindset was really important. And at this point in the world, we now have so many studies on mindset that shows that it improves people's learning, amazing work around improving people's health when they get health challenges, developing a growth mindset. They've done interventions where it helps students dial back on aggression. And so much evidence, but one piece of work I find really interesting was this study that was done with adults when they were taking tests. And what they found was when adults made a mistake in a test, those with a growth mindset, their brains were on fire with connectivity. That fiery-looking brain, they're actual voltage maps of the brains in the study. That's how much they saw of activity and growth when people made mistakes. If they had a growth mindset, those with a fixed mindset, they did not see that amount of activity. So I think this is a really important message for all of us. Excuse me a sec. As educators, we all face challenge and difficulty and struggle. Teaching is a really hard job. And what this says to me, what this study shows me, is if you go into those difficult times thinking to yourself, I can do this, but then you mess up or you fail, your brain will respond with more growth than if you go into those situations thinking, I can't do this. That growth mindset, that believing in yourself, so important for you as teachers as well as for our kids. And it helps make sense of this kind of evidence. This comes from one of Carol Dweck's studies. The only difference between these two groups of students was their mindset. They had the same teachers, but the kids with a fixed mindset, you see them on this low-level path. Kids with a growth mindset are on a whole different trajectory, going upwards. So on our website, UCubed, I apologize, it's either in English or Portuguese. We don't have it in Swedish. But we have lots of resources to help with mindset. There are surveys, of course, that we can use with kids, but this rubric really captures what it's like, what are the key behaviors of a growth mindset. So many teachers give this to students, maybe at the beginning or the end of a class, of a time with them. We also have a journal where students can really journal about and reflect, or you as teachers can reflect on important parts of mindset. But in the US, this is kind of where I think we are with mindset now. A lot of teachers have jumped on this mindset bus, and they're sharing with their students, you just have to work hard, keep going. But what I know, and what we know from studies, is when those mindset messages hit the wall of what I would call fixed maths, short questions with one right answer, with one method, those messages fall flat. Students can't see how they can grow and learn when they're doing worksheet maths. So we're all about, at UCubed, opening up maths to allow students to see growth. And another neuroscientist that we've found really interesting, I work with somebody called Vinod Menon, has published this, that when we think about something in maths, there are 5 different brain pathways we can activate. So at the back of the head, that green and orange are the visual pathways. All of these pathways we want to activate for students. And we know that the most successful people in the world are those who have more brain communication between these pathways. And we get that communication when we don't just see maths as numbers, but maybe also as visuals, words, pictures, graphs, algorithms, tables, modeling with maths, moving. All of these things will get this brain to be more active. So my new Mathish book shares this very interesting study. They looked at the brains of mathematicians, living mathematicians, and compared them with the brains of other academics. And what they see is more activity in the visual parts of the brain in mathematicians. They are using those visual pathways even when they're working on number or algebra. So I wanted to give you an opportunity to get your visual pathways active, and I'm going to give you a little maths question to think about. So my request for you as I share this is to think visually about it. Don't think with numbers or algebra, just visually. And just on your own to start with, in a minute we'll talk, but see if you can get your own thinking on this. So this is a growing pattern, and in case 1, there are some squares. In case 2, there are more squares. In case 3, there are more squares. And my question is, where on the shape do you see the extra squares? So think about that for a moment on your own. And when you think you see where the extra squares are, share with the people around you. See where they see the squares. So I love to watch people do this problem, because standing here looking out at you all, or I see all this gesturing like this. It's up here, it's down there. And when we gesture, and when you see students gesture in classrooms like saying a triangle, that shows you they're thinking visually, that the visual pathways are active. So I've asked lots of people this question, teachers, students, all sorts of people, and I know that everybody thinks differently about it, lots of different ways. So it was my undergrads at Stanford and I also ask students. When I do this with students, I give them little cubes, and I also ask them to describe their method in words. That also gets another pathway. So it was my undergrads who described this method as the raindrop method. They said it's like drops of rain coming onto the shape. Who saw it in that way? Also, my undergrads described this as the bowling alley method. They said it's like a new row of Skittles in the bowling alley. Who saw it that way? Very different from the raindrop. It was a teacher who said to me, I see a volcano. The volcano erupts and the lava follows. So we call that the volcano method. Who saw it that way? Some people see the launching of a rocket. The shape separates and a new center comes in. Who saw that rocket? Some people see a growth of triangles. The shape grows in a triangle shape. And some see the triangles that aren't there, which we might call the negative space in mathematics. We get regional and cultural differences. This one came from teachers in Boston, could have been Sweden actually. They said, oh, it's like when the snow melts and the buildings come out of the snow. And then this one was from a young man at Stanford. He said to me, I see the Minecraft tree. This is the tree, and this is how he sees the growth. He saw the growth. That kind of sideways growth. Did anyone see it in that way? And then this, always a favorite, you can move the red square, all squares, and you see that the shape grows as a square. Did anybody see it in that way? So this is what I want to illustrate with this question. In maths class, in algebra lessons, if we're lucky and there's a visual at all, teachers might give a visual like this, but then they ask the students, how many? How many squares are in case 1 and 2 and 3, or n, the nth case, as a way of thinking about algebra. And what happens is students count. So they'll say, well, in the first case, there's 4, and in the second, there's 9, in the third, there's 16. And then they're expected to stare at those numbers until they notice that if you add 1 to the case number and square it, you get the total number of squares. It's that n+1 squared. I gave this out in a big room of teachers once in the US, and one group of teachers didn't listen to my request to think visually. They were high school teachers, and they did this. They drew up a table quickly, they counted, they called me over, and they said, we've got it, it's n+1 squared. And I said, okay, why is it n+1 squared? And they were like, huh? Didn't mean anything to them. Because it's all symbolic. When we give this question to students, we just change it a little bit, and we ask them, how do you see it? And they come up with all these different ways of seeing the shape. Not only are they seeing it in these different ways, but they understand the function. If you look at the last one, the square method, you can see that the square is always 1 more than the case number. So in case 1, it's a 2 by 2 square. In case 2, it's a 3 by 3 square. That gives us the n+1 squared. Whenever we have a quadratic function, we can see the square somewhere if we show that pattern. Yet students in algebra get no insight, no experience of that beautiful visual algebra. We could come up with an algebraic expression for all of these patterns, and we would have a whole room full of different algebraic expressions, all of them equivalent to n+1 squared. So it's actually, you should try it. I sat with my colleague to try and come up with expressions for these actually once in an airport bar. And this is when we do our best mathematical thinking. We call it bar math. Very creative, but try it. It's pretty difficult, but very interesting. So we have on our website 4 weeks of algebra lessons that introduce algebra visually to kids. Free, anybody can use them. Beautiful, amazing visual algebra. But another couple of messages we shared with the kids in our maths camp, and I also share with my undergrads. Being good at maths does not mean being fast. Fast calculators doesn't mean anything for being really a good mathematician. And this is a really dangerous myth that holds kids back. We share with them lots of top mathematicians who will talk about how slow they are because they think deeply, they don't think quickly. And, you know, we all probably know students who get things really fast. But what the neuroscientists will say is important learning is always slow. When people learn things quickly, they're developing what they call easy come, easy go brain pathways. But you really want to learn something, it has to be slower and deeper. So how do you have time for this slow, deep learning that takes up more time? And one of the initiatives I've been working with in California is to teach maths as big ideas. I mentioned how in our camp we taught 4 big ideas. So we have taken all the content in every grade, the same content as you have here, and reorganized into these big conceptual ideas. And we say to teachers, make sure that you teach each of those big ideas through deep, rich tasks. Even if the rest of the time is textbooks, that will allow students to have a foundation that makes everything come together. In some of our work we're doing on number at the moment, we've done a really interesting new study that shows that what separates low from high achieving students, it's not how much they've memorized, it's number flexibility. How flexible are they with numbers? That is what we should be aiming for with kids. And in our framework in the US, we talk about number flexibility. It begins in the early grades, but it continues up through the grades. So I thought I'd show you a little example of this too. And I'm going to give you a number question. I'd like you to think about it in your head. We're going to do like a kind of number talk, and then we'll talk about it. So if I was to give you this question, how would you work it out? What would be your approach? So think about that for a minute. So I don't want to speed you, I don't want to rush you through it, but I want to show you some things. Some of you, probably, when you get a question like this, your approach is to line it up to use like an algorithm. Who does that? Who did that? Not too many. It's actually the hardest of all the approaches to do in your head. And when I do talks like this with parents, they will all tell me they did this. They tried to line up the algorithm in their head and calculate. Of course, there are many other methods, and I'm curious about how you would think about it. But when I do these number talks with students, I also visualize them. So a method that you might have thought of, some people do, is to say, I'm going to think about 20 times 5 and take off 2 5s. Who did that? And I would visualize it for students. Or maybe you thought about 10 times 5 and 8 times 5. Did anyone do that? We can visualize that. Or 9 times 5s, or 18s, or my favorite, did anybody think 18 times 5 is the same as 9 times 10? And visually, we can represent that in this way. When I do this with my undergrads at Stanford, they say to me, this is the first time they have understood why it works, that you can change 18 times 5 into 9 times 10. That 9 times 10 rectangle has the same area. So we can make everything visual in mathematics, and it's super helpful when we do that. So we haven't got too much time left. I wanted to share with you that reasoning is a really important it's a really important part of mathematics. And it is what mathematics is, really, sharing your reasons. And I wanted to share a little clip from a film that highlights reasoning, that's a new film in the US that I really like.
What people say about mathematics who have really studied it is that it is the music of reason. That is the language God has written the universe. It's a study of pattern and structure and form.
At its best, mathematics trains you to become better at changing your perspective and seeing the underlying essence of something. It's like making the invisible visible.
I don't think there's people out there who have never done math. I actually think we're all thinking mathematically all the time.
So, reasoning, you heard there that mathematics is the music of reason, some great words there. What amazes me is that when I look at textbooks inside the US, and I don't know what it's like in Sweden, they look like this. There is no reasoning to be seen. They say, fill in the answer, solve the question, complete this division. So when we work with students, we don't ask them questions like this. We ask them, how do you see it? Why does that work? Can you prove it to me? We have a framework that we find really helpful with students I want to share with you. It's called the Skeptics Framework. We tell students reasoning is really important, but there's different levels of reasoning. At the lowest level, you might convince yourself of something, a little bit harder to convince a friend, and the highest level of all is to convince a skeptic. And then we say to the students, we want you to be the skeptics. And I can tell you that middle school students willingly became skeptics. They embraced it. We also told them that, in maths, you should come up with your own conjecture. I don't know what word you have for that in Sweden. It's like an idea you want to test out. So I want to share a little clip with you of a student in our camp coming up with a conjecture and reasoning, and you'll hear the students being skeptical with each other.
Yeah, I mean, so odd numbers equals an even number.
This is your conjecture, Matt. That every two odd numbers make an even number. Yeah. Who agrees with that? I know, it's exciting. Who could give me a visual proof of this? Anybody? Josh, come on.
Yeah. So say 1 is, it's odd, and then 2 is even, and 2 plus 2 equals 3, and 3 is odd. And if I were to do 1, which is odd, plus 1, which is also odd, it would equal 2, which is even, plus 0. And this works for everything. The end.
Why does that work?
Prove it, John. You want me to prove it? Yeah. I will do 201, which is odd, plus 1,103, which is also odd. And I will end up with 1,304, which is even.
How do you know that?
Because you can divide it by 2 and it will split into 2 even numbers.
You probably noticed there, as the students were saying, how do you know that? Prove it to me. Why does that work? The more they were skeptical, the more the student reasoned, and the reasoning comes out. So we don't have much time left. I do want to share that, we really also made a big effort in our camp to have kids have physical objects to help them develop really important mental representations. These are important at every grade level we teach. If you go to our website, you'll see lovely tasks in calculus, where kids are actually holding objects in their hands and seeing what they mean. So one last thing before I leave you. We have an online tool now that you might find useful. It's called Struggly, to encourage kids to struggle. I developed this with a German design firm who are amazing at making the mathematics really beautiful and visual. And students get to try these different activities. And then they get badges for making mistakes and for thinking deeply. Most apps really just reward speed. Our app rewards kids making connections. And so try it. It's at struggly.com. You can. It's too beautiful to be on a phone. It's not big enough. But iPads, computers, most of the tasks have no words, so great for Swedish learners. And they look, this is an example of a little one, they focus on kids understanding how numbers are made up. And yeah, we also, as I said, we have a book series. We have a new thing that's coming to UCubed, which is we're inviting people into our community where they get to have a whole year of engaging experiences. So that's coming up. Keep an eye on that. And I have books. So if any of you would like to read more or get in a little bit more depth on these ideas, these books are for you. So thank you for being here, and enjoy the rest of the conference.